Good evening. Good evening. Please silence your phones so we can hear the speaker. I'm excited tonight to introduce Carrie Fitzgerald. She is the director of the Observational Observatory and Planetarium at Montgomery College. Graduated from University of North Carolina at Chapel Hill. Her husband is here and works at NIST, so there's lots of relationships here.
Yep.
And she's going to tell us, after Frank has tried to get an astronomer in the building for 3 years, here's Carrie Fitzgerald.
Oh, thank you, Doug. Oh my goodness, thank you so much for letting me come and speak. I am so excited to be here, and I really want to thank Doug and Kathy and Frank and Dave and all the other folks here who have helped me get here and paved the way for this presentation. But again, I'm so excited to share something that I love so much, astronomy. So I've been teaching at Montgomery College for about 15 years now, and I primarily teach introductory astronomy. I host observatory events, and I also host planetarium shows in our brand new planetarium on our Tacoma Park campus. And when Doug reached out to me to give an astronomical talk, I was super excited because he gave me freedom. I could talk about whatever I wanted, which is a little dangerous sometimes. So in preparing for this talk, I wanted to share sort of how our view of the universe has changed over history. And it ended up being kind of a big talk, and it's changed a little bit in different iterations, but I do hope you enjoy the things that I have thought to include. So we'll get started. So I wanted this to be a talk about instrumentation and telescopes and how telescopes have changed our worldview. But I realized before I can talk about telescopes, I need to talk about the before times, before telescopes. So I want to give you a little prelude to instrumentation before we had telescopes, as many years that we as humans just looked to the sky with our naked eye. Now on this figure here, see if I can get the laser pointer. I don't want to upset. There we go. So I have this very unique looking pattern. I don't know, when I was a little kid, we had a toy called Spirograph. And that's what this reminds me of. What this is a model of our universe. The model for our universe that we've had for centuries was an Earth-centered universe. And it was beautiful and nice to be at the center of the universe. And this was at a time where the heavens were meant to be perfect circles, perfect spheres. But there are a lot of observational problems with Earth-centered universe. So I will ask, any of you watch the stars? Can you get outside, look at the stars, look at the planets? Yeah? All right. Yeah, excellent. Right? If you watch the planets long enough, you'll notice something kind of wacky happens to the planets. They will, appear to move one direction relative to the stars for a while, and then they'll change direction. They'll move backwards. It's called apparent retrograde motion. Now, we understand what causes it now because we, have existed in our sun-centered universe for so long. But for years, people tried to figure out what was going on. And this was one of the ways they explained it. They put the Earth at the center, and then they put the planets on these little loops, these little complicated loop-de-loops like a spirograph. And it worked for a long time. I will say that what people wanted from the time of the ancient observers, the ancient Greeks, to this time period where I'm highlighting here in the 1500s, people wanted predictions. They wanted to know, when am I going to see Saturn near Jupiter? When is Venus going to be rising at a particular time? They wanted to know these things. So people worked hard on developing data tables. And to develop those data tables, they, came up with these wild models. They worked okay, but not great, right? It was not the best situation. All right, so I've got two beautiful models. Sometimes I just love the artwork from this time period, right? So the model on the left is a Earth-centered model with Earth at the center and then everything orbiting around our planet. And I imagine it did feel good to be at the center of the universe for a while. But as I mentioned, this model wasn't working great. There were issues where, the predictions wouldn't work out. So in the 1500s, there was a gentleman I'm going to talk about, Nicholas Copernicus, who went back to this really old idea. This went back to 1700 years before Nicholas Copernicus, when Aristarchus had the idea to put the sun at the center. Now you might be wondering, like, why the heck did they get rid of this idea? Somebody thought about it in those times. Why didn't we just keep it? The problem was they didn't have any observations to prove the model. They didn't have any observations that they could show that Earth was actually moving. And the simpler model does seem to be like, yeah, we're at the center. We're gonna go with that. But I'm gonna show you that eventually we did change. Again, this is Nicholas Copernicus. He was a Polish mathematician and astronomer. He was from a pretty wealthy family, and he really wanted to sort out this problem that folks were having with these data tables. So prior to Nicholas Copernicus, maybe about 200 years prior, there was a Spanish monarch, Alfonso, who tried to work out these tables. He got so frustrated with it. He was like, oh, if I had been around at the moment of creation, I would have made it a lot simpler. And I can relate. It's complicated. But Nicholas Copernicus, although he did not invent the idea of a sun-centered model, he did work out the mathematics, so he's credited with being the first one to work out the mathematics. But he made one choice that wasn't great in the mathematics. This is his book on the revolution of the heavenly orbs. Unfortunately for Copernicus, he did see the publication of this book, but it was on the day he died. So he only got to enjoy his being an author for a day. All right, so this is the Copernican model that we're familiar with, where we have a sun-centered model, and we have all the planets orbiting around it. The problem with Copernicus's model is, he used perfect circles. Can you blame him, though? I mean, the heavens, they're supposed to be perfect. Because he used perfect circles, the observations did not match his model. They matched okay, but not great. And so he ended up doing all this nonsense to try to make it work. And he ended up even adding back in like those little epicycles, the little spirograph stuff. And so even though his model was beautiful, elegant, got the sun at the center, it's the right model, people really didn't accept it because they were like, oh man, we've been using Ptolemy's model. This is the guy who had the little spirograph. We've been using Ptolemy's model for years. Why would I want to switch to this model that doesn't even work that great, right? So it was elegant, just not that great at the predictions, unfortunately. Really, what was needed was more data, right? I know there's a lot of scientists in the room who are probably understand that desire for more data. But at the time, again, we are in the 1500s. The telescope has not yet been invented. We're still in our prelude phase. So all the data we have is naked eye. It's just measuring positions of the stars and the planets on the sky, on the celestial sphere. Astronomers measure positions on the sky using angular measurements. So the idea is to have specialized tools to measure with as much accuracy as possible. So the greatest naked eye astronomer in history is this gentleman I'm showing right here, Tycho Brahe. Has anybody ever heard of Tycho Brahe? Oh, yeah, you guys are with me. So you might know some of the crazier stories about Tycho Brahe. So credit where credit's due. This guy knew what he was doing when it came to astronomical measurements, but it was also a little different. I'll tell you some stories about Tycho Brahe. Of course, the one most folks know about is about what happened when he was 20 years old. It was nighttime. I have a feeling he was probably drinking, and he got in an argument with another dude about like a math problem, right? And so now, like these days, like you get in an argument with somebody about like a little math problem, you pull out your phone, you look it up, like, okay, you're right, I'm wrong. But this is the 1500s. Dudes get in an argument, the swords come out. It's a duel, right? So Tycho is dueling with this guy at night, and he ends up getting his nose cut off. Oh, yeah, I know. And he had to wear like this prosthetic nose. So I think it was like some sort of alloy. Apparently, he had more than one. He had like a good nose, like a gold one that he would pull out for those special occasions. But then he had like the daily nose, I guess. So that was Tycho Brahe. Tycho Brahe. Yeah, exactly. I like that, business and casual. So Tycho Brahe, really, he was also kind of arrogant, and he had his own ideas. Tycho Brahe had an idea about the universe that was different than everybody else's. So we've been talking about Earth-centered and sun-centered and that big debate. Not for Tycho Brahe. He's like, I'm putting the Earth at the center, and then I'm going to put the sun orbiting the Earth, but I'm going to put all the other planets orbiting the sun. So he had this entire solar system orbiting Earth in his model, which is like, wow. Nobody took it seriously, but Tycho Brahe really worked to get the data to prove this model. And here's his model that I'm talking about, right? So Earth is at the center, and then we've got the sun, and everything else is orbiting around the sun. And that whole system goes around. It's a little wild, but that's Tycho Brahe for you. So Tycho Brahe, he managed to convince the king of Denmark, Frederick II, to give him some money to build this really rockin' observatory on an island off of Denmark. And Tycho designed this observatory. It had the best equipment. So these are a couple images. This is from Tycho's own book. You see he has it aligned north, south, east, west, all these little buildings. And then this is Tycho Brahe in his beautiful golden observatory. He had all the best tools of his day. But again, no telescopes. What he's doing, he basically has a giant protractor, and he's measuring angular positions on the sky. And what Tycho was able to do that nobody else had been able to do was to measure these positions with a 1 arc minute resolution. So an arc minute is a very small angular measure, and I'm sticking out my hand like this because an arc minute is basically, if you stick out your hand, your fingernail's width is an arc minute. So that is how close he would be able to measure two celestial bodies to one another and resolve them. So it's pretty impressive for the day. So he did some good work, and he got a lot of data, all in service to trying to prove his model of the universe that I just shared with you. So I could honestly, I could probably give like a whole semester talk about Tycho Brahe. He's just fascinating. Like, he was a great naked eye astronomer. Yes, he lost the nose in the duel. We covered that. Oh, I haven't told you about his pet elk. Oh, no, he had a pet elk. So he also had a lot of big parties. He was a big drinker, big partier, and he had an elk for entertainment. He also had a person living at his observatory with dwarfism that he thought had like some sort of second sight or ESP. So we'd have this guy Jep like read people's fortunes at these parties as well. I mentioned he drank a lot. He wasn't the best guy. I mean, he slept with a lot of people's wives and had a lot of illegitimate children. That was Tycho Brahe. So it's quite possible that he died because he was murdered. So his death is interesting too, because of course it is. It's Tycho Brahe. Tycho Brahe was at a banquet, and he needed to use the bathroom, but he decided that it would be rude to stand up and use the bathroom. So I guess he waited a little bit too long. Then when he got home, he couldn't pee, and things went downhill from there. So the common idea was he probably had some sort of bladder situation happening. But later people started wondering, like, did somebody poison Tycho because he had so many enemies? He, like I say, slept with some people's wives, and so some scholars thought that Brahe was poisoned because he slept with the king of Denmark's mother. So there is a lot, and this isn't the only suspect for who could have killed Tycho Brahe, but Danish scholars did exhume his body. They tested his hair, and they tried to figure out he had been poisoned by mercury or arsenic, and it doesn't seem that he was. It seemed like he did actually die of natural causes, despite the fact many people did honestly want to murder him. including this guy. But this guy, this is Tycho Brahe's assistant, Johannes Kepler. So Tycho Brahe knew that he wanted to do more with his data, but he needed help. So he hired this younger guy, Johannes Kepler, who is a much different personality. So these two kind of didn't get along all that great. Where Tycho was boisterous and loud, Kepler was quiet and mystical. And he also, too, poor Kepler, he had his own little problems. His mom was arrested for being a witch, and so I'm not even kidding. So his mom was arrested for witchcraft, and so poor Kepler has to like leave his job and try and defend his mother. And this trial for his mom lasted 6 years. Yeah, and there's no evidence that she practiced witchcraft. I've read different accounts. Some folks think that she may have been like practicing midwifery, so she would have had some sort of potions and medicines and whatnot. Others say, well, she just liked to make some nice teas for herself every once in a while. I mean, what lady doesn't? But this got her into trouble. She was accused of witchcraft, and in her 70s, this poor woman, they arrested her. She was in prison. She was basically in a leg chain for a year, this poor lady. Yeah, but Kepler did his best to defend his mom against witchcraft, but that's not supposed to be telling you right now. The story I'm telling you right now is about Kepler and his analysis of Tycho Brahe's data. Now, Kepler had been hammering on this data, trying to make it fit the Copernican model. Kepler did not believe in Tycho Brahe's model. I don't blame him. He was trying to make the Copernican model work, and he just struggled with it. Oh, he struggled, especially with the orbit of Mars. It was driving him nuts. It was off by like 8 arc minutes, hardly anything at all. Man, if I were Kepler, I would have been like, dude, Tycho Brahe was drunk the night he took the Mars data. We just need better data. Like, I don't trust it. But Kepler did trust Tycho Brahe and his data. So he just continued to work and work and work and work on the problem. And finally, the answer came to him. So this is what he says about his when he discovered it. He says, if I had believed that we could ignore these 8 minutes of arc, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore those 8 minutes, pointed the road to a complete reformation in astronomy. I wish I could have seen the look on Kepler's face when he finally figured it out, because the solution is really simple. It's just that it's not circles, it's ellipses. And an ellipse is kind of like a squished circle. And once Kepler realized that the planets aren't on perfect circles, they're ellipses, everything fell into place. And now we're able to make data tables that are accurate, right? And we can predict when Jupiter and Saturn are going to be next to each other, or when Mercury is going to transit the sun. So this was a reformation in astronomy. Like I said, I would have loved to see the look on his face when he figured it out. Okay, so that was still a prelude. I'm finally going to take us now to the invention of the telescope, which it was invented in the early 1600s. Galileo is generally credited, but he did not invent the telescope. It was invented by a Dutchman, Hans Lippershey. Now, what's puzzling to me is why the heck it took so long for us to get a telescope as humans. There have been spectacles, glasses in existence since the 1300s, but we got to wait 300 years to get this telescope. Now, stories differ about how Hans Lippershey came up with the idea. In one story, he sees 2 kids playing with 2 lenses, and that they like have this aha moment when you put the 2 lenses together, you can magnify something. But the true story is lost to time. So Galileo may not have invented this telescope, and at the time it was called a Dutch perspective lens, or Dutch perspective glass. The name telescope came a few years later. But Galileo was able to improve the instrument, right, so that it worked out better. And he is credited with being the first guy to put it up in this, look at the heavens with this telescope. Galileo he made some major discoveries with this telescope that finally, once and for all, got us to the Copernican sun-centered system. He published in 1610 Sidereus Nuncius, or the Starry Messenger, and that is the reason why this idea became popular. My own kind of belief in this is that it became popular because Galileo was also an amazing artist. He was like one of the first people to do some really beautiful drawings of the moon, the planet Jupiter, and the Jupiter's four brightest moons orbiting around, also known as the Galilean satellites or the Medici satellites. So his artwork was quite exquisite. Sorry, and a little bit of an aside with these beautiful moon images that Galileo drew. His images even changed how religious art was drawn. So prior to this, there would be beautiful paintings of the Virgin Mary standing on the orb of the moon. Prior to Galileo, that orb was completely, flawless, a perfect sphere, no shadows, nothing. After Galileo, artists started incorporating craters on that moon, which is kind of cool. Oh, here he is presenting his device to folks in Venice, convincing them it would be useful also for, looking at enemies coming from the sea too, like not just for astronomy. And he was trying to convince folks that the sun-centered model was the correct one. And he was given a harder time than Copernicus was, because Galileo was a little bit more bombastic and jerky about it than Copernicus was. So this is another drawing from Sidereus Nuncius. One of the observations that Galileo made that really kind of once and for all told us we are not at the center. Galileo observed the phases of Venus with his telescope. The only way to see phases that look like this of Venus is if the sun is at the center, and then you've got Venus orbiting the sun, and then you've got Earth orbiting the sun outside of that. And so you can see this is his drawing, and here's like the actual phases of Venus that he observed. I hope at some point y'all can come to my planetarium, because I have a kind of a fun show that goes through Galileo's observations of those Jupiter moons. With a planetarium, you can take the sky back to 1600 to see what Galileo is actually seeing. And since Galileo's records still exist, right? We have his logbooks, we have Sidereus Nuncius. We can compare what we saw, or what he saw, to what we would see if we were standing next to him in 1610. All right, so we're moving forward in time. So just to review, we've got ourselves firmly established that we are not at the center of the universe. We also have established that Tycho Brahe's model is not the correct one, and we have a telescope with which we can start to make some real observations. So now I'm moving us into the 1700s, and once you have an invention like the telescope, of course, people are going to improve on it, make it better and better. So we get to look at the sky through bigger telescopes, and we begin to think more about this place that we inhabit. Do you ever think about mapping the Milky Way? Yeah. Man, I know, right? It's such a problem. How do you map something when you're inside of it? Yeah, it's a little bit like, go into somebody's house that you don't really know, and maybe that person, they stick you in their closet, and the only way they'll let you out of the closet is if you draw them a map of their house. I know that's a really weird analogy, but that's kind of what it's like for us in the Milky Way. We're embedded in this island of stars. How are we going to actually figure out our place in that island of stars? How do we map it? So a brother-sister team, the Herschels, in the 1700s took on this project. And let me tell you about good old William Herschel. Man, this guy liked to build telescopes. So I'm going to show you a drawing of one of Herschel's telescopes. He Man, he made like over 600 telescopes. And again, this is the 1700s. It's not easy to make a telescope, especially the mirror has to be perfect. It's got to be smooth and stuff tarnishes. It was a lot of work. He sold them too. He sold about 60 or so telescopes. King of Spain bought one for like 3,000 pounds at the time. So he was able to make a little extra cash from his telescope side gig. But one of his projects was to map the galaxy, and he and his sister did this together. And what I'm showing you, I know it's like you're wondering, what is that thing that is on here? This is actually their map. So what they did is they counted stars. They just looked up into the sky and counted stars. Well, I will ask you all, have any of you been to a location where you could see the band of the Milky Way? Oh, that fills my heart with joy. So many of you, I ask my college students this question, and most of them have never seen the Milky Way. Yeah, right. And like, so then I have to explain what it would look like if you could get to a dark sky site. So I'm so glad that a lot of you have been able to see it. I imagine that the Herschels didn't have too much problem seeing it because they're doing this in, the 1700s. All right, so this is like, if you've not seen it, this is the idea. When you go outside from a dark sky site, you will see what looks like clouds. They're not clouds, they're concentrations of stars in a band. And the reason we see the Milky Way as a band like this is because our galaxy is shaped like a pancake. So now in your mind's eye, envision a really wonderful, fluffy pancake. All right. So everybody got the pancake? Yeah. Okay, good. So us orbiting the sun, we are inside of the pancake, right? We're in the pancake. So whenever we look around like this, we just see more pancake, right? But if we look up or if we look down, there's less pancake for us to see. So what the Milky Way looks to us from inside of the pancake is like this band, the band of the pancake on the sky, right? And so what the Herschels were doing, were trying to count the stars in that pancake and map our place inside of it, right? So if there's like more concentration of stars over here than over here, that would tell us something about our location. So it's a really good idea. Good idea. Good on the Herschels, right? Oh, and here's one of Herschel's telescopes. This is his 20-foot telescope. Now, I know some of you know a bit about telescopes, and normally when an astronomer tells you the size of their telescope, they're talking about the size of the mirror, right, or the size of the lens. Herschel's telescopes were talking about the length of the tube. So at the time, the quality of the mirror wasn't that great. So normally the way a telescope would work, you'd have a mirror down here, like the main mirror. Light would come in, then it would get reflected back up here, and there'd be another little secondary mirror up here that would push the light back out, and you'd have an eyepiece down here. You've probably seen like that. It's called a Newtonian design because it's invented by Isaac Newton. Herschel had his own ideas. You see this little platform here with this little bar stool? Yeah, he didn't use like an eyepiece down here. He just looked in the tube at the image, yeah, because the secondary distorted things too much. The mirrors weren't that great anyway. So that was Herschel's way of doing things. I say bravo. So this was the telescope he primarily used with his sister to map the Milky Way, to do those star counts. And this is kind of a long quote, but I love Carolyn Herschel, and man, sometimes you just want to like step back into history and wish that you could be there and like watch all this unfold. So she's like describing like a day in the life of like trying to work with her brother when he's doing all this crazy stuff with making these telescope mirrors. And so she talks about the day. A day was set apart for casting, and the metal was in the furnace. But unfortunately, it began to leak at the moment when ready for pouring. And both my brothers and the caster with his men were obliged to run out at opposite doors, for the stone flooring, which ought to have been taken up, flew about in all directions as high as the ceiling. My poor brother fell, exhausted with heat and exertion, on a heap of brickbats. I don't know what a brickbat is. Before the second casting was attempted, everything which could ensure success had been attended to, and a very perfect metal was found in the mold, which had cracked in the cooling. So can you, I just imagine like all the time, the energy, and like just how challenging all this was. And Herschel made, like I said, he made 600 mirrors. He was really, it was like, he was into it. He was serious about his telescope habit. All right, so we've got the Herschels. We're mapping the galaxy. What the Herschels found in their map is that the stars of the Milky Way seem to be evenly distributed, right? That there's not more over here and more over there. The Herschels found clearly that, yeah, the Milky Way is shaped like a pancake, but we're in the center of the pancake. That was their conclusion. So we might not be at the center of the solar system, but it seems like, at least for now, we're at the center of this island of stars. Whatever it is that this island of stars is, we're at the center of it. Now, like, kind of spoiler alert, we're not at the center, right? But the data showed that we were. It took some time. So I'm fast forwarding us now to the 20th century, when we've got some like major telescope action going on, and we can start to figure out where we are. I love this guy too. Harlow Shapley. He's awesome. So he was born in 1885 in Missouri, and he must have just been brilliant. So he dropped out of school like after the 5th grade, and he was trying to get, odd jobs and what, but he got frustrated because nobody would hire him because he didn't have a high school education. So he enrolled in a program, like a 6-year program, to get his high school degree. He finished it in 2 years, and he was valedictorian. So smart guy. So he wanted to go to the University of Missouri, and he was intent on studying journalism. He gets to the college, and he finds that the journalism school is closed for a year. Yes, that's sad, right? When you what you want to major in, and you can't do it. So as Shapley tells the story, he says he just opened the catalog to A, and like, okay. Astronomy. He did like astronomy as a child, so it seemed like a good major, and clearly it was. Shapley is credited with figuring out our position in the Milky Way, and he figured out our position in the Milky Way using those beautiful objects. I've got one in the background. This is a globular cluster, so I want to talk about globular clusters because they're some of my favorite things to look at. They're beautiful. All right, so go back to your pancake. Wherever you put your pancake, bring it back. We got the pancake. Surrounding the pancake in this spherical halo are like these balls of sugar around the pancake. These globular clusters in our Milky Way galaxy are in this enormous sphere around the disk. They contain hundreds of thousands of stars. They're almost like little mini galaxies that are orbiting our galaxy. Now, we see globular clusters like this in other galaxies too, other spiral galaxies like our Milky Way. We've got about 150. And these objects, they're beautiful. If you've ever seen a globular cluster through the telescope, they're just gorgeous. There's a couple that you can see with the naked eye if it's dark enough, but they're amazing. I love globulars, not just because they're pretty, but because they're useful. Globular clusters are the oldest stars in our galaxy. There are stars in these globular clusters that are like 12 billion years old. And what's amazing about that is that, well, you know how like an archaeologist will dig up old stuff to figure out what was going on with like ancient people? Like, astronomers want to do the same thing. We want to dig up old stars so we can figure out what our galaxy was like when it was young. So these globular clusters preserve the elemental abundances that our galaxy had when it was young. They preserve the motions that our galaxy had when it was young. They're fossils, essentially, these beautiful objects. But they also orbit the galaxy, and therefore orbit the center of mass of our galaxy. So Shapley's idea, Harlow Shapley had the idea, like, okay, if I can work out the center of mass of these globular clusters, I'll work out the center of our galaxy, right? So it's a clever idea. So now this the thing is you got to map these clusters, right? So now we're not mapping the individual stars, we're mapping these 150 globular clusters. All right, so going back, this is a Herschel's map, right? Got the sun at the center there. I don't know what was going on with these two little leg things, but that's their map. That's okay, right? I kept the map here, but I added Shapley's data. I added Shapley's globular cluster data. So what I'm showing you here is those little white orbs are the globular clusters that Shapley measured their distances. And if we work out the center of mass of those clusters, we find that the center of the galaxy is here and we're here. Right? So yeah, like once again, we've been moved from our privileged place. But you can't blame the Herschels, right? The Herschels didn't do anything wrong, right? It's our galaxy that's got the problem. Our galaxy, the pancake, has got a lot of dust and stuff that blocks our view. So the Herschels couldn't see past that gas and dust, so they couldn't count all the stars, right? But Shapley, being able to measure those globular clusters, finally put us in our place, right? Now we know where the center is. Okay, so this is actually the next two slides I'm going to show you are from my astronomy class, because I make my students do a lab. So I'll tell you, my astronomy class meets during the day, so we don't actually use a telescope for our labs. I have them use a computer software program that simulates the night sky. It's like a desktop planetarium program. You should ask me about it later because it's free. And so if you are interested, you gotta download it. Okay, so what I have my students do is I have them measure the positions of globular clusters in the sky and plot them on a star map. Yeah, so let us pretend that we are standing in the center of the galaxy here. Okay, there's our pancake, and these are our clusters. If you're standing in the center and you're looking all around at these clusters, I want you to imagine in your mind's eye what that map is going to look like, right? What is it going to look like to you if you started plotting all of those clusters? Hopefully in your mind's eye, something like this. Like they're all over the place, right? Because from the center of the galaxy, everywhere you look, you see clusters, right? So if we were at the center of the galaxy, which we're not, but if we were, we would see globular clusters evenly distributed in the sky. All right, now we're gonna change things up a bit. Okay, now I'm gonna put us where we actually are. We're about 2/3 of the way out, okay? So now if you look out of the galaxy, you don't see many clusters, right? They're just because you're looking out. But if you look in towards the center, you see a bunch. So now I want you to imagine what that map is going to look like when you make the plot. You probably figured it out. Yeah, right? All those clusters are mostly concentrated on one side of your map. This is exactly what we observe. This is what my students figure out. The center of that distribution is towards the center of our galaxy. It so happens that if you wanted to fly to the center of the galaxy and you had a spaceship and you could do so, go in the direction of Sagittarius. That is your way to get to the center, right? Because we, sadly, are not at the center. Oh, so problem with doing astronomy from where my observatory is located in Rockville is that stuff looks pretty fuzzy. I mean, even if you do have a nice sky sight, oftentimes those deep space objects that we look at just look like little fuzzies, right? Even a galaxy, is it a galaxy? Is it a cloud of something? Is it a smudge? What is it, right? It's hard to tell what some of this stuff is. So again, I've got us in the 1900s, right? We're starting to build larger telescopes, but the telescopes of the early 1900s were still not powerful enough to observe individual stars in galaxies beyond our own, right? And, in this time period that we've been talking, I've moved us from center, no, yeah, maybe, right? If we could get better telescopes, maybe we could figure it out. I don't know. Let's see. All right, so here again, I've got my fuzzy galaxy. That just happens to be the Andromeda Galaxy. The Andromeda Galaxy is one of our neighboring galaxies. It's relatively close to us, and you can see it from a dark sky sight with your eyeball. If you have a small telescope, it does look kind of like that fuzzy photo I showed you a minute ago. So in the beginning of the 1900s, the telescopes could see these objects as nebulae or clouds, but they couldn't see individual stars in these galaxies. So astronomers didn't know if these clouds were part of our galaxy or like other galaxies, right? And it seems like a simple question because now we know, yeah, there's lots of other galaxies. We're just one. But in the early 1900s, it was a really big question. Like, how big is our universe, right? Is the Milky Way, are we at the center just by being in the Milky Way? What do we do? All right. Well, we debate it. So again, my buddy Shapley, right? He's around. He debates with another astronomer, Curtis, in 1920 in Washington, D.C. And the debate is this question: how big is the universe? Is our universe the Milky Way and that's it? And we're in it? Or is the universe bigger and we're just like one little island of stars? So both of these guys had data to support their views. So Shapley thought incorrectly that the Milky Way is the entire universe. That's it. All this other stuff we're seeing out there, it's all the Milky Way. It's all the universe. Curtis was a no. And what's interesting about this debate, both guys had data. They had both published papers on this, and they both had ideas for why they were right. The end of the night, the debate was a draw. Like, nobody left thinking that they knew the answer, because what was needed was more data, like, once again. And what was needed was an ability to actually see if these galaxies were outside of our Milky Way. Okay, so enter these two gentlemen. And I started having like way too many slides. So there are other pictures of people that I would want to put up here. So I'm gonna talk about a couple guys that I didn't include on this slide. So again, early 1900s, Edwin Hubble. You've probably heard of the Hubble Space Telescope. Yeah, Edwin Hubble gets like a lot of credit for measuring the distances to galaxies, right? His partner there is Milton Humason. So let me tell you the story about Milton Humason and Hubble. So this is early 1900s. Hubble is offered a job at the brand new Mount Wilson Observatory in California. Biggest telescope of the day. But Hubble goes to fight in World War I first, before he comes back to take his appointment. When the observatory is being built, they're carting up materials with mules. And one of the guys who worked on that was this guy, Milton. Milton lugged stuff up the mountain while the telescope was under construction. After that, once the telescope was built, he got a job as a janitor in the observatory. After that, he was promoted to be a night assistant. So he just kind of helped the astronomers with their work. And he was so good at it, they just made him an astronomer there. And he was Hubble's collaborator on data that I'm going to show you that changed the world, changed our perspective on the universe, right? But I will say that Hubble gets a lot of credit for something that was measured prior. So I'll get there, I promise. Oh, and here's the beautiful 100-inch or 2.5-meter Hooker telescope on Mount Wilson. The biggest telescope of its day. It was constructed in 1918, and it was the largest telescope in the world until 1949. There's also the smaller 60-inch telescope that was used by Harlow Shapley for that globular cluster data that we talked about just a minute ago. All right, so with this amazing telescope, Hubble and Humason found that the Andromeda spiral, because we didn't know it was a galaxy at the time, the Andromeda spiral was actually beyond the Milky Way. So this was the first paradigm shift, right? Okay, so now we have evidence that we are not the universe. The universe is bigger than us, and the Andromeda galaxy is outside of it. So, okay, great. All right, so Hubble and Humason continued to try to measure the distances to other spirals or other galaxies. And they found something wild. They found that the farther away the galaxies are, the faster they're moving away from us, right? This is a big deal. But again, Hubble wasn't the first, and Humason, they weren't the first. They published this work in 1931, but there was an astronomer in 1914, Vesto Slipher, who made measurements at Lowell Observatory in Flagstaff. I don't know if you've heard of Lowell. He was kind of a wealthy guy, a little eccentric. He was kind of obsessed with like finding life. Like we know Lowell from his like drawings of like canals on Mars and all that. It's that guy. And he had hired Slipher to measure the spectra of these spiral nebulae or galaxies to try to figure out if there is life there. He was looking for signs of life in these spirals, which was really, the telescope was not set up for that. But Slipher did it, and he measured the distances and the velocities of these galaxies, and he found this data in 1914. So this is some 15 years before Hubble and Humason published their work. So the bottom line here is that we have this situation where the farther away the galaxy is, the faster it's moving away from us. All right, so what does that mean? Oh, okay, what does this mean? It's important. Here's the data. This is from their 1931 paper. And I think I promised a couple people that there would be data. So here's some actual data. This is, yeah, I know the scientist, engineer folks out there, like, show me the data. This is the velocity of the galaxy. This is the distance the galaxy is from us. Each one of these little circles is a galaxy. Linear relationship, farther away, the faster it's moving. Okay, so when I show this to my students, I get all excited about it, and they're just looking at me like, why? Why are you so crazy? This is why I'm crazy. Because this was another paradigm shift. What Hubble and Humason had rediscovered is that our universe is expanding, that space itself is expanding, right? It's incredible, right? Now, when I was a young sprout and I first learned about the expansion of the universe, I totally did not get it. I was like thinking that like the ruler is expanding and oh my God, I'm expanding. Not good, not good. But that's not what's going on. It's not us or any of the galaxies. It's just the space between galaxies that's expanding. But it's pretty wild, right? Space is expanding. I mentioned that Slipher had first observed this in 1914. And then in 1920, there was a Belgian priest, Georges Lemaitre, who worked out kind of the physics of this and had proposed an expanding universe in 1920. But he published it in French. And it was in this like relatively obscure journal. Nobody wanted to read the French. And so he doesn't get a lot of credit for it, but he really is the one who did the thing. Okay, so I know I'm rapidly running out of time, and I just got a couple more big observations that changed our view of the universe to share with you. You all know about gravity, right? Yeah, oh, it's a pain in the butt a lot of the times. But gravity tells us that, the closer two masses are to one another, the stronger the force. And we can think about that in terms of our own galaxy. If we are a star that's near the center of this massive region here, we should be moving faster, right? And if we're a star farther out, we should be moving slower, right? That's what happens in the solar system. Mercury moves faster than Uranus does, right? Because Mercury's closer, gravity. But wow, were we wrong? Yeah, so again, I've got more plots. So this is like fake data just to show you. So if physics worked the way we expect it to, and it generally does, you would expect stars that are close to the center of our galaxy to be moving faster and then taper off as we move far away, right? That's what we would expect because that's gravity, physics. Oh man, imagine observing that and being like, gosh darn it, did Tycho Brahe take this data? What's going on, right? Yeah, what we observe are flat we call these rotation curves, the velocity versus distance of these stars. So we observe a flat rotation curve, which is insane. Like, if you think about it, it means like something is like way wrong with our understanding of gravity, or there's something really wonky going on with our galaxy in the mass stuff. So what this curve implies is that the mass that we see with our eyeballs is not the mass that's all there. There's more mass that we're not seeing and we can't detect. There's something wacky going around in not just our galaxy, but in other galaxies too. So Vera Rubin is credited. Yay for Vera Rubin. We love Vera Rubin. You know, she taught at Montgomery College. Yeah, she taught some stuff. I think also she took like a Fortran class at MC with my colleague. So this is Vera Rubin at Kitt Peak. She's credited with making this discovery. She measured these rotation curves of not just the Milky Way galaxy, but several other galaxies, leading us to this amazing discovery. And this is from her 1970 paper. So again, we have the rotational velocities, it's the velocity of the stars versus the distance to the center of the galaxy. And we see that they don't taper off. If physics and gravity were what we would expect, it should be high up here and low down here, right? But that's not what she saw. And so she's credited with discovering this thing. What does it mean? Dark matter. Have any of y'all heard of dark matter? Yeah. It's crazy, right? And honestly, I would have thought by now we would have sorted this. It's been decades, literal decades. So much so that now there's like a lot more people thinking that we're getting the physics wrong and that what we need to modify is our understanding of like gravity over larger distances. I can't speak to sorry. Okay, so now we have mass in our galaxy that we can't observe. Things are nuts. Time moves forward. Hubble Space Telescope changed our view of the universe, really, I think popularized astronomy. Like I said, I'm running out of time. I'm going to talk too much about this. So I will bring up this beautiful image. This is one of my favorite Hubble Space Telescope images. It's called the Hubble Ultra Deep Field. Imagine looking at the sky with a drinking straw that's 2.5 meters. Okay, yeah, that's what Hubble did. Very small section of sky, and in that section of sky is like 10,000 galaxies, all sorts of amazing, beautiful galaxies. There is I couldn't fit the whole thing on my screen, so it is cut off a little bit, but you can see there are a couple of stars in the foreground, and you know they're stars because of those crosshairs. And that's an artifact from the telescope itself, from the secondary mirror that's being held to the top of that, the top of the telescope. So 2 stars and the rest are all islands of stars, right? Okay, so Hubble Space Telescope, we could find galaxies up to 10 billion light years away. That's amazing. Great. So now we're going to have another paradigm shift, and it's the last one, I swear. I won't shift anybody's paradigms beyond this. The paradigm shift that we got is that not only is our universe expanding, not only is the space between galaxies expanding, but it is expanding quicker and quicker and quicker. The expansion is accelerating. Wild, right? How the heck? What? How is that even happening? Well, and how do we know this? So, kind of long story short, we know this because we have telescopes like the Hubble Space Telescope that can measure distances to galaxies that are billions of light years away from us. And if we can measure their distances and we can measure their velocities, we can figure out what was going on a long time ago in our universe. And the reason that is because of the finite speed of light, right? Whenever you look into space, you're looking back in time. If a star is 10 light years away, you're seeing it as it was 10 years ago. If a galaxy is 10 billion light years away from us, we're seeing it and what the universe was like 10 billion years ago. So we are unable to see the future. right? We can only be in the now. We can't see, we don't have any data for the future, but we have data from the past. And these are all measurements to galaxies at different distances. And the curve I've put up for you here is of a universe that is accelerating over time. If you took my astronomy class, I would have walked you through the other models for our universe and made you sit through that. But so be lucky, you only get one model of the universe. It's the most interesting one because it means space is accelerating. But what's causing this? I don't know. And nobody knows. We say that what's causing the acceleration of space is dark energy, but we don't know what dark energy is. Nothing to do with dark matter. It's just dark because it's dark to us. We don't know what it is. What's kind of wild to me is that this stuff turned on a few, several billion years after the Big Bang. Don't know why. I don't know. Maybe it'll turn off. Maybe it'll reverse. You got me. But that's what's going on right now. And this has consequences for the ultimate fate of our universe. Right. Okay. And so present day, we have a lot of exciting data coming in from the James Webb Space Telescope, which was finally launched in 2021 after lots and lots of delays. And with that telescope, oh my, well, there it is. You've probably seen it, little hexagons. There we go. This one of, the most famous. So this is called Pillars of Creation. Hubble took this photo as well, same region of sky. It's about 7,000 light years away. It's a region of star formation. But it's just showing how our view, can you imagine showing this to Tycho Brahe or Copernicus or one of those dudes? They'd be like, what? I don't believe it. This is incredibly beautiful. So I always like to kind of finish presentations with this slide because it's a favorite. I'm wondering, does anybody recognize this? Yes. Oh, you guys, you fill my heart with so much joy. I just feel like y'all get me in a way that I'm normally not understood. So thank you. Yeah. So this is Earth. So when Voyager was out by Saturn, Carl Sagan had the idea of well, let's go back and look at our planet. And it's kind of an accident that it looks like this, is these little pieces of sunlight. It looks like a little piece of dust and a mode of sunlight. And if you ever want to feel I don't know, some emotions, listen to Carl Sagan read from his book, Pale Blue Dot. He talks about this picture, about how this is everything. This is all of us, everything that's ever existed, right? From Aristarchus to Tycho Brahe to us, it's all here. And how we fight and we go crazy for just a little fraction of this dot here. So yeah. Okay, I know I've taken up way too much time. I just get too excited because you guys are so awesome. So I will take questions.
Wait for a microphone. Okay.
Okay. 1, 2, 3. From your dynamic presentation, I imagine your students in your class would be so appreciative of having you as their professor.
Oh, thank you. You're so sweet. Thank you.
My question, I lived on a barrier island in South Carolina.
Oh, nice.
And on a cloudless night, you could see millions of stars.
Yeah.
My only disappointment in moving to Maryland is I look up at the sky and I see maybe 3 stars.
Yeah. I feel your pain, my friend. Yeah. Yeah, we need the big switch to turn off the power every once in a while. Yeah. Light pollution. Mm-hmm.
Yeah.
Thoughts about the Antikythera device?
No. Do you want to tell me more? The demise of
The thing that was found off an island off Crete
Oh no, I'm gonna have you gave me a research project now.
Yeah, it was found in a shipwreck,
Uh-huh.
dates probably to several hundred years BC, and apparently measures things that are
Oh,
just
is this the
incredible.
mechanism?
Yeah, the mechanism.
Yes, the mechanism. I know what you're talking about. Yeah. It's awesome. Like I want it. Because it reminds me of like an astrolabe, like an ancient astrolabe. And yeah, it's kind of amazing what people got up to when they didn't have television. I mean, I don't know. I mean, I don't have any like insights about it other than I think it's like really cool. Yes. Yes.
So I know you're dying to tell us the name of the app that we can see the night
Yes.
sky.
Oh my
Yes.
gosh. I'm sorry. I got to calm down. Yeah. I will send. Yeah, I will definitely send Doug the link. But it's called Stellarium. Stellarium. So for your desktop, it is free and it will run on Windows, PC, Mac, Linux. For the phone, I think the app costs a few bucks if you want it, because it's like the phone for or the app for your phone like is one of those like point me apps for the sky. But the desktop version is a full-blown planetarium software program. It's open source. I use it for all my astronomy laboratories. I use it for fun. Yeah, I will definitely. I will send you the link so y'all can play with it. Mm-hmm.
One more question here.
It's hard to understand acceleration of the universe, but the accelerated expansion is really mind-boggling. I suppose. What do you think? Is that the dark energy somehow must be growing and expanding too for the universe to expand? Is there any sense to it?
There's no sense to it. Yeah, it's completely mystifying. Like what started it? Why did it turn on? Like I say, what we do know with it is what we can predict, and that it predicts like an end of the universe. That's kind of sad, right? Everything is just going to spread apart. Eventually, all the stars in every galaxy will die. Eventually, any action that can happen will have happened. All the black holes will have evaporated with Hawking radiation. There'll be nothing. And at that point, the end of the universe is really an end of time. Because when you think about what time is, it's marking one moment to the next, like the tick of a clock or your heartbeat. When the universe is like has no action, time is done for us. So it's kind of a depressing end to the universe. Like, fingers crossed, maybe dark energy will turn off. I don't know, or change direction. Then we would have a more interesting fate. Yeah. Yeah, sorry.
Professor?
Yes.
Ma'am?
Right here.
Oh, where are we? Oh, okay.
Thank you. When I look at the night sky and I see the constellations and all that, and think back for millennia, people have been navigating by the heavens, and the
Yeah.
stars are more or less where they've always been.
Mhm.
But with the galaxy rotating and flying through space, how are the stars not scattered about? Why are they all still in the same place so that we can still navigate?
Okay, yeah. So you are correct. They do appear to be in the same place, with some exceptions. We can measure the motions of stars. Thing is, like, it just takes a long time, right, for us to see the motion. There's one star, Arcturus, in the constellation of Boötes, that does have like a reasonably high, we call it proper motion when it moves across the sky, and we've been, you can actually track that over a lifetime. But most of the stars, yes, they're objectively moving fast. We're moving with them, and in the end, it's just too slow for us to see over the years that humans have been on, doing navigation. Now, that being said, like, I don't want to get off on a tangent, but there is an effect called precession where our planet wobbles, right? And that does shift where the constellations are in the sky. So as far as like navigation stuff, that can, mess with things a bit. But the star's motion is just not enough. Like, we're not here long enough to really see it. It's a great question.
Okay, let's thank Carrie again.
Yay! Thank you. Thank you.